Okay. First, can people read this at all? No one can read it? Those with excellent eyes? Okay, so maybe I will make this bigger. Let's see. Okay. And wait a minute, that didn't work. No, because I have to zoom in first, so let's see. Wait, why did it do that? Oh, but it does work. I just didn't click OK. Okay. And this you can read. Okay. So I'm basically going to start going through this this draft, which I want to stress again that you can get online. So if you just go to the summer probability school for the last school I taught, I don't know, maybe I could get Bendelin to email this, or someone who has the email could maybe email this link to the group. Yeah, okay, that would be great. Yeah, they said it would take a few days because they have to print it in Rio, but yeah. But anyhow, this is available online, and it's so it's still in draft state, but it's here. Okay. And so again, I said last time, the main idea is we want to be showing that if you glue two quantum gravity surfaces together, the boundary between them is an SLE. And as we prove this, we'll find all sorts of nice symmetries of the construction that turn out to be very natural if you believe that this construction comes from discrete quantum gravity as a scaling limit. So let's see, so this I already said. So okay, so I want to highlight really two ways of generating this random geometry from the Gaussian free field. First, there's this Liouville quantum gravity, which is where you take mu h to be e to the gamma h of z dz, where h is the Gaussian free field. And we have to make sense of this as a limit in the way I discussed last time. And the second is this AC geometry. Okay, so now I'm going to start writing some of these things on the board. So how do we define this measure? So if H is the Gaussian free field, then my measure mu equals mu sub h is what I'm just going to call the limit as epsilon goes to 0 of e to the gamma h sub epsilon of z dz. Okay, so here this limit means a weak limit. So these are measures. So this here is a measure that's absolutely continuous with respect to Lebesgue measure. And I'm taking mu to be the limit of these measures. So it's not the limit of these functions here, it's the limit of these measures. Each of these measures is well defined as a measure on my domain D. So let's make this a Gaussian free field on a domain D. And so as epsilon goes to 0, I want to say we get some limit. And, well, if you wanted to actually prove that this limit exists and start understanding things about it, you really have to understand what these h epsilon z's are, their covariances, and so forth. So one of the first things we'd like to do is ask, I'm sorry? What's that? Yes, sorry, that's right. It should be epsilon to the gamma squared over 2. Thanks. Right. Okay. So first of all, I don't know. So last time, did you do the covariances of these guys? So you know the covariance of, yes. In terms of integrals, right. But I guess what I want to stress, so if you did this last time, this will be a quick review, which is that so in general, remember the variance of h, Dirichlet inner product of function f, is equal to the Dirichlet inner product of f with itself. And h epsilon of z is equal to the Dirichlet inner product of f with a particular function, which I'll call psi epsilon sub z, where this, well, in general, we have this fact that the Dirichlet inner product of f and g is just the L2 inner product of f with minus the Laplacian of g. So this this here should be minus Laplacian inverse of the uniform measure on a circle. And you can work out what that is. So this is going to be equal to, well, it's, I guess, minus the log. So let me say this function here, where psi epsilon sub z is equal to, so I'll say this, in a minute, there's this g tilde sub z. So if I evaluate this at a point y, this is equal to g tilde sub z of y minus, and it's going to be the log of the maximum, let's see, of epsilon and z minus y. Okay, so basically, I have my domain D, I have my point z, I have a ball of radius epsilon, and there's going to be a function which is essentially the log of z minus a point. So it's has a logarithmic singularity at this point z, except for I do two things to it. So I take the log of z minus y, and I do two things. The first thing I do is I chop it off at epsilon, an epsilon ball. So this, taking the max of epsilon in this, corresponds to chopping it off here. And the second thing I do is, well, I want the boundary, I want this function to be 0 on the boundary. So I just subtract off the harmonic extension of this log function. And that's what this thing is. So I don't know if you used this notation last time. Maybe something else. But this is what the Green's function is. The Green's function is minus the log, except that then you have to subtract the harmonic extension of minus the log. So view this as a function defined on the boundary, and then subtract its extension to the interior. And you get something which has 0 boundary conditions here. Okay, so and now if I wanted to compute something like the covariance of this at one point with this at another point, say I want to compute for you the covariance of h epsilon 1 z1 with h epsilon 2 z2. Well, this, now we know what it is. It's this Dirichlet inner product of these critters. So it's psi z1 epsilon 1 Dirichlet inner product psi z2 epsilon 2. But then I can use my friendly integration by parts trick and take minus the Laplacian of one of these guys. Remember, by definition, each of these guys is Laplacian inverse of this uniform measure on a circle. Right, so this is equal to psi epsilon 1 z1 of Dirichlet inner product with minus the Laplacian of psi z2 epsilon 2. So this here is the uniform measure on the circle of center z2, radius epsilon 1. So this is just equal to the mean value of psi z1 epsilon 1 on the boundary of the ball of radius epsilon 2 centered at z2. Okay, and okay, and you know what this is? So let's assume that z1 and z2 are such that the circles don't overlap each other, and they're both contained in the domain D. So if this happens, then, well, okay, this function here is harmonic, at least outside of this little ball. It fails to be harmonic on the boundary of the ball, but it's harmonic everywhere else. And harmonic functions have this nice property that their value at a point is the same as the average value on a circle centered at that point. So this is just equal to the value of this function at z2. This is equal to psi z1 epsilon 1 at z2. But now, what is this psi 1 really? It's a truncated Green's function, right? I took the Green's function and I essentially chopped it off at this epsilon. So this is just the Green's function from z1 evaluated at z2. So this quantity is what we call the Green's function of z1 with z2. Okay. So this could not be simpler. In the sense that if I want to know the covariance of this guy, h epsilon 1 z1 with h epsilon 2 z2, as long as the circles don't overlap, the epsilons are irrelevant. And the covariance is simply the Green's function of z1 and z2. And that Green's function is essentially the log of the difference between z1 and z2, except that you have to subtract this stuff so that, you know, if I fix z1, view the thing as a function of z2, it vanishes on the boundary, and so forth. But, okay. So that's it. And, okay, so this is kind of nice, because it means I have a very simple tool for computing covariances. And that also should help me if I want to compute things like means and covariances in higher moments of these guys, of the e to the gamma h sub epsilons. So this is a random function here, e to the gamma h sub epsilon of z. And unlike many of the random functions one encounters in statistical physics, this is a random function that you can compute everything about. You can compute its mean, its variance, its higher order moments. You can compute any moments you want, and it's all easy. Okay, you should savor this moment, because this doesn't happen often. So why is it we can compute all these moments? Well, it's because it's just a Gaussian, and Gaussians are easy. So if n is a normal random variable with mean A, variance B, then the expectation of e to the n is equal to what? Let's see who can be the first to do this calculation in their head. E to the a plus b over 2, that's right. Okay. Yeah. I mean, it's just the, it's just this complete the squared trick, right? The expectation, you're taking this integral of this e to the minus x squared over 2, 1 over root 2 pi dx. And if you want to compute the expectation of e to something times x, then you put in an e to the what's that? X minus a squared. Yeah, that's right. If I'm doing the mean, x minus a squared. And then, well, I can make this over, well, okay. I'll let you finish that. I'll just say it's easy. Right. So easy computation, the expectation of e to a normal random variable is e to its mean plus its variance over 2. So how does that help us? So what if I want you to tell me what's the expectation of mu sub epsilon of a set? Let's say call this set S. What is that? Well, okay, it's going to be equal to the integral over S of the expectation of epsilon to the gamma squared over 2 times, well, what? So what's the variance of one of these guys? Well, the variance of h epsilon of z is, so here we need to do a slightly different calculation because this circle overlaps itself. I mean, I'm taking these two things to be the same, so I can't view them as non-intersecting circles. But it's essentially the same thing. If I had this at the same place, then when I got down to here, I'd be saying take the average value of this on this circle. So I'd be looking at just the circle here. And what I get is just the value of this log function minus this harmonic extension of the log on the boundary. And that value is sometimes called the conformal radius. So what I get here is essentially I get minus the log of epsilon, and then I have plus the something called the conformal radius. I should say plus the log of this conformal radius of z and d. So don't worry about this too much. This is just some function which is a continuous function of z. But the point is, and I guess you did this last time, that the variance of h epsilon of z is going like minus log of epsilon, which means that this thing here is a Brownian motion when you parametrize time by minus log of epsilon. Okay, so knowing this, we can now compute. So it's the expectation of this. Well, okay, we already know it's times e to the gamma h sub epsilon of z dz. But now we have some hope of computing what's inside here. Because the expectation of e to something, this is a Gaussian random variable, of mean 0. Well, it's just e to the variance over 2. So this piece in here is simply e to the what? Well, so maybe I'll put this part out first. So it's epsilon to the gamma squared over 2 times e to the that thing over there, variance of h sub epsilon of z over 2. Variance of gamma h epsilon of z over 2. Okay, but this variance here we can compute. And then, yeah, well, I just bracketed out this piece here. Sorry, I like to use brackets. So while we're in the business of brackets, let's bracket this piece here. What's that? So the variance so this thing here, the variance, e to the variance of gamma h epsilon z, so the variance is just going to be gamma squared times what we have over there. So this is just going to come out to be, this will be e to the gamma squared over 2 times minus log epsilon plus log of c zd, which is just equal to, so this epsilon comes out. So it's e to the, it's just epsilon to the minus gamma squared over 2 times c zd to the gamma squared over 2, if I did that right. And okay, so this part is going to cancel with this part. So the whole thing, so if I call this star, then in the end what I get is that star is equal to, so this cancels this out, and it's just equal to c of z d to the gamma squared over 2. So in other words, the expected amount of area, well, sorry, star, it's the integral of this. dz. And a nice thing you see about this is it doesn't depend on epsilon. So it's just the way we chose to regularize by replacing h with its average value on a circle is a way that makes everything extremely simple. This h sub epsilon of z is just a Brownian motion in minus log of epsilon, a regular old Brownian motion. All of the means and covariances are very easy to compute. And now if I want to compute something like the expected measure of a set, mu epsilon of a set, then, well, it's clear. It's just, it's a nice integral that doesn't depend on epsilon. Okay, now here's a question. What if I remove the epsilon? What's the expectation of mu of s? Anyone have a guess? Okay, well, I mean, our guess would be obviously that it's the same thing. But that's not quite a proof, because you can have a sequence of random variables that all have some expectation, but they converge to something with expectation 0. You know, like if you have a martingale and you start it at 1 and you run it until it first hits 0, you know, at each finite time its expectation is still 1. But if you run it long enough, you know, if you run it all the way to infinity, the limit is almost surely 0. So it's not immediately obvious that in the limit you get a random measure whose expectation is this. And in fact, you don't if gamma is 2 or bigger. So it turns out there's a range of gamma for which you have the appropriate tightness, uniform integrability, that you need to show that this limit exists. So I'll say fact. If gamma is between 0 and 2, and I'll always assume that's the case in these lectures, then expectation mu s is equal to the expectation mu epsilon of s, which is this formula I just derived. Okay, but now let's suppose we want to accomplish even more. Can we compute some moments? So let's see. Oh, there's one over here too. Okay, well, I'm still learning this. Okay, so let's see. Okay, so let's say we want to compute the expectation of mu of S1 times mu of S2 times mu of S3. This is a triple moment. It's like an event in the Olympics. Can you compute this triple moment? Well, so what are you going to do? Well, let's put in epsilons and do this for epsilon. Actually, what we're going to have is an integral over S1 times S2 times S3. And then we'll have this expectation of, well, epsilon to the gamma squared over 2 times e to the gamma h sub epsilon x. Well, I'm going to have 3 of these guys, so I'll cube this. E to the gamma h epsilon y, e to the gamma h epsilon z. And now I'll have dx, dy, dz. So now I have an expectation of e to this times e to this times e to this. Okay, but h sub epsilon of x plus h sub epsilon of y plus h sub epsilon of z is still a Gaussian random variable. Right? The sum of 3 Gaussians is still Gaussian. And we know what its variance is. It's just the, what's the variance of the sum of 3 Gaussians? Well, it's the variance of this plus the variance of this plus the variance of this plus the sum of the covariances of all the pairs. So this is just equal to, and we know what the covariances are. So assuming, say, these 3 guys are disjoint, so let's take D and I'll have S1, S2, S3. If they're nice and disjoint like that, and epsilon is small enough, so it can't intersect both of them at once, or more of these than one of these sets at once, then we're going to know just what the covariances are. The covariance of this and this will just be the Green's function. So we're just going to get an integral of this epsilon to the 3 gamma squared over 2, and then we're going to have, well, we're going to have 3 variances, which are going to more or less cancel out this guy. So the variance of this is going to be what we put over there. So I'm going to have this conformal radius x in d to the gamma squared over 2 times this log epsilon term, which is essentially going to cancel out this. And so these 3 variances are all going to cancel out this. So let me just erase this. So we're going to get c y in d gamma squared over 2 c z d gamma squared over 2. And then I'm going to have these Green's functions. So this, so the covariance of this with this is just the Green's function. We can have the Green's function of x with y. And then I'm going to take e to that. So I have e to the 2 times the Green's function xy times e to the 2 times Green's function yz times e to the 2 times Green's function xz. Okay, and these three functions, Green's functions, are essentially logs. So essentially what I get, this will be something like the log of the difference between the two. I mean, this is e to a log. So I'm just going to get the difference to some power, distance to some power, difference to some power, times some nice smooth functions here. And so I'm essentially integrating differences to powers. Okay, but the point is it's a nice formula. It doesn't depend on epsilon and is easy to compute. Okay, any questions about these calculations? Yes? If the S on I's are not disjoint, well, I mean, you can still make sense of this. Because for most epsilons, things are not going to overlap. It's only going to be in the small case where the epsilons come into be in the same place. So if you could show that that contribution is small, then it's still going to be the same thing in the limit. So it'll still work when they're not disjoint. One trouble is when they're not disjoint, you might get infinity, depending on what gamma is. So it's not always the case that, if gamma is large enough, then then mu of s will have an expectation, but it won't have a variance. And and there's some threshold of gamma for which it will stop having a third moment, stop having a fourth moment. As gamma gets really small, you'll have all these moments. But I mean, again, it's just let me. Let's see. So yes, there should be. Did I miss a gamma squared? So yes. So this should be. All these should have gamma squareds over 2. That cancels this 2. So you get something that is that looks kind of like this integral of x minus y to the, is it just gamma squared then? To the minus gamma squared? Right. Times y minus z to the minus gamma squared times z minus x to the minus gamma squared. So it's something like this, but then you have these other terms here, but these are all just nice continuous functions of x, y, and z. But the relevant question is this integral finite? And you can just sort of do the calculation yourself. If x, y, and z are in a little set, and you try to integrate this out, you get something finite or infinite. And depending on the value of gamma, there will be a phase transition in gamma where you start having this integral being finite or infinite when you have 3 of these guys. And that will tell you when the third moment stops existing. Okay. So that's that. We have a lot of very nice tools at our disposal in Louisville quantum gravity. Everything is nicely computable. Now I want to say something about what happens if we try to change coordinates in Louisville quantum gravity. So I'm erasing this. Maybe I'll return this over to here. Okay. So let's say I have a domain here, D, and I have a domain here, D tilde, and let's say I have a conformal map from D tilde to D that I'll call psi, and I have a Gaussian free field H over here. And that means over here I can take H composed with psi to give me a field over here. Now we know that the law of the Gaussian free field over here is the same as the law of the Gaussian free field over here. Now the question is, if I look at mu sub h as a measure on D, and mu sub h composed psi as a measure over here, how are these guys related? And what if I really wanted these things to be the same measure? What if I really wanted this to be the, this measure here to be just the pullback of the measure over here via psi? How would I need to tweak this function to make that the case? Well, okay, at first glance, this is just a problem that we have all taught our first-year calculus students. We're just changing variables. And so you know that you have, there's some Jacobian here, right? Your space is getting stretched out over here. And if you want the integral of this function over here to be the integral of this function over here, you have to somehow, you have to scale by the derivative squared or something, right? Okay, so that would suggest that, if we're integrating e to the gamma h over here, e to the gamma h composed psi over here, well, maybe we should kind of multiply this by something like psi prime squared. Did I get that right? I always get these signs wrong. So if this is, if psi is stretching things out by a factor of 2, then maybe I want to divide. Maybe I want to take this minus 2. Does that look right? No one's willing to help me out. So, right, let's see. If psi takes this and multiplies it by 5, then if I take the integral over here, it would be smaller. So I think I have to multiply this. I take psi prime squared, and then the integral over here will be the same. Right? I think h is the constant 1. Psi is multiplication by 5. It works, right? Okay. People are looking very suspicious. This isn't meant to be the hard part. Okay, so right, so I want to multiply by this psi prime squared, but it's actually a little more than that, because if you think about what I was actually doing in these things over here, I was multiplying by an epsilon to some power. So over here, I take an epsilon to the gamma squared over 2, and over here I had an epsilon to the gamma squared over 2. But when I map from here to here, the epsilon over here is not the same as the epsilon over here. The epsilon also gets changed. Which means if I want this number here to agree with this number here, I also have to account for the fact that this is a different epsilon. And so if this is stretching by 5, then the epsilon also gets stretched by 5, which means that over here I'm computing with an epsilon that's 5 times bigger So I'll get a 5 to the gamma squared over 2. So in order to get this to be the same, I have to multiply this by psi prime to the gamma squared over 2. Okay. And this says if I define h tilde to be h composed psi plus, and now I'm going to take the this log of psi prime so I'm just going to take the log of this piece. This would be so times 2 plus gamma squared over 2. But I'm taking e to the gamma times h. So I'm going to want to make this a, I'm going to want to divide by gamma here. So I divide by gamma. If I divide this by gamma, I get something that's called q. Q is defined to be 2 over gamma plus gamma over 2. So this 5 plus q times the log of psi prime. Okay, so that so if I do this, then I indeed have that mu sub h tilde is the pullback of mu sub h, i.e. mu sub h tilde of a set A is equal to mu sub h of psi of A. So this is if I want to take the same quantum surface, again, I have in mind that there is some surface out there, and I've conformally mapped it to D, and E of the gamma h is just telling me the area measure in D. So if I want to parameterize that same surface with a different domain D prime, then this is the boundary. A smooth function that goes to something non-zero at the boundary. So I'm going to claim that that smooth function is not in the Hilbert space closure of the set of zero boundary functions. Okay, now you're right that takes some proof, right? It's not obvious. You could think maybe this is in the Hilbert space closure. I mean, but this is not such as, essentially in order for the function to get to be big right near the boundary, the average derivative between here and where it gets big has to be pretty large. And when you integrate that, it's going to be something big. So maybe I'm not going to write out these details, but it's pretty easy to see that any smooth function that's non-zero on the boundary is not going to be in the Hilbert space closure of the smooth compactly supported functions. Okay. Let's see. I guess I don't have screen anymore. Now it turns out that it's rather simple to explicitly compute Green's functions for the free of fixed boundary field on the half plane. And so it's worth working that out. Okay. So if I wanted to define the whole plane Gaussian free field, how would I define that? So this is a field on C. Well, so I can define the Gaussian free field on all of C just the same way as I would on any other set if I'm doing free boundary conditions. It'll just be a random field modulo additive constants. And but I'd really like to understand if I take H inner product with row 1 and H L2 inner product with row 2. So I want to take the average. Maybe this represents one weighted average of the field and this represents another weighted average of the two field. What's the covariance of this, of these two numbers? And well, first thing I know that if I'm dealing with H being only defined up to additive constant, then row 1 and row 2 better have total integral 0. Otherwise, there's no way this can be defined. Because if I add 5 to H and the total integral of row 1 is 7, then I've just added 35 to this number. So if this is only defined up additive constant, I'd better have row 1 and row 2 only have integral 0. So right now I'll put a question mark here, and I'll say assume that the integral of the row I z dz over C is equal to 0. Okay, you can take these to be smooth, compactly supported, nice as you want for now. I just want to compute the covariance. And so we want to use our usual integration by parts trick. So I know this is going to be equal to somehow, if I take minus Laplacian inverse of row 1 minus Laplacian inverse of row 2, and take the Dirichlet inner product of that, which is the same as sort of taking the L2 inner product with minus Laplacian inverse of row 1 and just row 2. And we know what this is. This is minus Laplacian inverse of rho is just this Green's function integral. But in this case, on the whole plane, how do you take minus Laplacian inverse? You just use the log instead of the Green's function. There's no boundary condition to worry about. So this comes out to be the integral of minus log of y minus z dy dz, and this is over c times c. And I should put in row 1 y, row 2 z, dy dz. I guess you did this calculation last time? Yes. Not in the whole plane, but it's the same thing you did before. You just had a Green's function here. And the way you defined this is as an integral. Basically, you integrate out this first part, and you get this. You integrate minus log y minus z, rho 1 y. You integrate out y. You get a function of z, which is minus the Laplacian inverse of rho 1 Okay. So we have this nice formula. And here it's nice because we don't have any boundary terms. It's just the log. And there's kind of a cute way that I like to go from the whole plane version to the half plane. And okay, and that's this this idea that if you have a field H defined on the whole plane, you can write it as a sum of even and odd parts. So I'm going to take this field H, so I'm going to write it as H even plus H odd, and even means H even of Z equals H even of Z bar, and H odd of Z is equal to H odd minus H odd of Z bar. Right, so I have this free field defined on the whole plane, and I just break it into two parts. There's the part that is where it's equal up here to its reflection here, and the part where it's odd. Okay, I'm sure you've all seen this sort of thing before. And then the idea is, well, the even part, when you restrict to the half plane, is going to be the free boundary Gaussian free field, and the odd part will be the zero boundary Gaussian free field. This here is kind of by definition, it's forced to be zero along the boundary, because h of 0 has to be minus h of 0, so it has to be 0. And this can be anything on the boundary. So this piece here is only defined up to additive constant, like this piece, or this piece here is defined without additive constant. And okay, so now if I ask you to compute something like the covariance of h odd, row 1, with h odd, row 2, well, you would know really how to do that, because if you think about it, h odd row is just the same thing as so something like root 2. Let's see, how do you do this projection? So it's okay. I mean, it's essentially h of row minus h of row star, where this is just row reflected over the axis. And then possibly times some, 1 over root 2 or something if we put that in. I mean, we can do whatever we want, right? But I want to, I guess I'll put in a 1 over root 2 because I want these things to have the same sort of local variance structure that this has. Okay. And So what I'm going to end up getting is that this is equal to the integral of rho 1 y rho 2z times g yz dy dz, where in this case the g, I could call it g odd or g free or something, or sorry, g, maybe g0, g zero boundary free field. I'm just going to get that this is, well again here, this is actually just regular old h integrated against two things. This is h integrated against two things. So the product of those guys then has 4 elements. And I can put those 4 elements into here, and I'll get this, will be something like the log of y minus z plus the log of y minus z bar. Okay, so this is this is all right here in section 3. So let's just check and get the formula correct. So I see, yeah, so I did put in a square root of 2 in my definition of h odd and h even. And so I get h odd against rho is 1 over root 2, h rho minus rho star, h even against rho is 1 over root 2, h rho plus rho star. And then when you actually write everything out, what do you get? So just using that thing over there, h odd rho 1, h odd rho 2. Well, remember, each of these things has mean 0. And they're Gaussian, so I'm just looking at the expected product of these guys, and so I can write it out. It's the integral over h times h of this thing here times this thing here. That's just using the formula I have over there, and okay, I can just. Okay, so getting from here with this value, I guess everyone can see that. Okay. Right, there's just some symmetry that if I just had a rho 1 over here and I replace it with the rho 1 star over here, that would be equivalent with replacing the x here with an x bar. So I think of this as a sum of 4 different things, where I take either rho 1 and rho 1 star over here, and I take either rho 2 or rho 2 star over here. And each one of those 4 things is equivalent to taking rho 1 here, rho 1, 2 here, but then in the log, you take x minus, well, either x or x bar minus either y or y bar. And then, and so you get 2 terms that are the same. X minus y bar is the same as y minus x bar. And x minus y is the same as x bar minus y bar when you're looking at the magnitude of it. So those things combine and you end up with just 2 terms. And then the half-plane Green's function. With free boundary conditions, you just get these things having the same sign instead of opposite sign. So, if you didn't like the whole introduction that Mendel and I have given to the Gaussian free field, you could just start with this. And some people in physics actually do that. You just start and say, okay, I'm going to define these random variables, h inner product with rho, and I'm going to give them this covariance structure. Covariance between this and this. They're going to be Gaussian, and they'll all have mean 0, and the covariance will just be what you get with this Green's function, where in one case you take minus log x minus y bar, minus log x minus y, and in the other you swap the sign of one of those. Okay. So, but one thing I want to take from all of this is that if you look at the boundary of the whole plane Gaussian free field, you have a little bit more variance than you have in the middle. Okay, how can we sort of make sense of a precise statement of that? And of course, this thing is not a function. In particular, it's not a function on the boundary. But let's say I'm in the half plane, and I take the average value on this semi-disk minus the average value on this semi-disk. Okay, so these two things are well defined, because I'm taking one average minus another average. So that's something that doesn't depend on the additive constant. So if I look at the average of this minus this, so let's say this is radius 1, this is radius of epsilon. What is the variance of that? And if you think about it, the thing that computes this average minus this average will just be a function which is, I'm taking the Dirichlet energy against a function which is constant out here. It goes logarithmically up here, and then it's constant in here. And you can compute the Dirichlet energy of that. And or you can also compute this by using this formula we have here. You take the integral over all pairs of this guy. And what you see is, when you have something like this, the integral coming from stuff here, integrating over this, it sort of contributes twice as much. Because when points are near the boundary and near each other, we know that when x and y are close, it's big in the zero boundary case. But if x and y are close and they're close to the boundary, then this is sort of doubly big. It's big for two reasons. One, because x and y are close, and one, because x and y bar are also close. And if you just take this difference, I guess you could even do this directly using our definition of h even. What you'll find is that the variance of h epsilon of a point, say, 0 on the boundary is now, and again I have to be careful, I have to put h epsilon minus h1 of 0. Okay, now this is going to be equal to, well, so before it was minus log epsilon, and now it's minus 2 times log epsilon. Okay. The point is, it's not such a drastic change. So along the boundaries, I have a kind of a similar covariance structure. I understand what's going on. Now, this is useful. In fact, I really understand these free boundary fields, because now, if we go back to the beginning, you can show that if I try to define a measure on the boundary of the domain, by mu h is the limit epsilon goes to 0, then I can make a boundary. Again, I can take e to the gamma h epsilon of z. But now, I'm going to divide this by 2, and then I have to take here a different normalization factor because the boundary motion is going twice as fast. So first, I've divided by 2. That in itself would give me a different factor. It would replace the gamma squared over 2 with gamma squared over an 8. But then because the boundary motion is going twice as fast, I get gamma squared over 4. But you can check that here again, with the expected length along the boundary is well defined. It doesn't depend on epsilon. And everything sort of just works, just as before. I can compute moments of this boundary length, quantum length. I can show that as long as gamma is between 0 and 2, this thing exists almost surely. The whole story goes through exactly the same way. There's a version of KPZ for this boundary measure. Everything kind of works. So I'm telling you now is that if you have a quantum surface, oh, and also if you transform using this transformation rule with the Q, then this thing transforms correctly. Okay, so a quantum surface is a pair d comma h modulo this transformation rule, where I change to d tilde h tilde. Now what I'm telling you is that both area and boundary length are well defined for this surface. So a quantum surface, it may not be a surface in the usual sense. You know, it's not a smooth manifold. It's not a surface as it's usually defined in differential geometry classes, but it, my golly, it has a conformal parametrization, it has a length and for the boundary, and it has an area. Now, one thing it lacks that I have here in a friendly footnote is we still don't know whether the interior of a quantum surface is a metric space. So if you just restrict to the boundary, I mean, there's a length measure, so it's sort of a metric space, you know, if you're just required to move along the boundary. But I don't know this is a metric space. Well, how should it be a metric space? I mean, a pair d comma h, it is a metric space parametrized by d if for distinct x and y and d and delta greater than 0, I just define the distance from x to y to be the smallest number of Euclidean balls in D of mu h mass delta required to cover a continuous path from x to y. So, you know, I give you this delightful quantum surface. It's, I've got a D with an H here. I've got a measure on it. And I give you 2 points, x and y. And I just ask, you know, how many balls do I need? If the balls are required to be of size delta in this quantum measure, how many balls does it take for me to connect x to y? Okay, that's some number. And this is now a metric space, if I just use this as my metric. Okay? So people say, you know, quantum surfaces, Louisville quantum surfaces are not known to be metric spaces, but they are, see? There's a metric. Well, okay. It's not quite a metric on a quantum surface. The reason being, so first of all, it depends on delta. And what we would really like is to show that, you know, there's some limit that doesn't depend on delta. So you'd like to show that there's some constant beta that the limit as delta goes to 0 of delta to the beta d sub delta exists almost surely. The other thing is that it's not quite obvious that this definition here is invariant under coordinate changes. Well, it's not quite obvious, but it's almost seems morally like it should be obvious. Because if I map this to a domain d tilde, then these Euclidean balls get mapped to things that aren't exactly Euclidean balls anymore, but they're very close. If the size of these balls are small, then they're close enough that I should be able to tweak all the balls a little bit and have everything still work. So it certainly is believable that when delta is small, this distance is essentially invariant under coordinate changes. But what is not obvious is that you get a limit as delta goes to 0. Okay, so let's just say a quantum surface is this object, this pair dh modulo transformations. It has well-defined length, it has well-defined area, it has a conformal structure, and it is probably a metric space. But we don't have a proof. And this is a big open problem. Show that, yes? And we don't know what beta is. Even Bertrand doesn't know. The physics community has no idea what beta is. We know what beta is if gamma squared is equal to 8/3. Gamma is equal to kappa. That corresponds to the pure quantum gravity case, where you, and in that case, it's 4-dimensional. So, yeah. So they know what it is. I mean, we still don't have a proof even of that case that this thing converges, but at least we know what the beta should be in that case. But in general, no idea. It's sort of vexing. I mean, you know, we've had some late night discussions, various people trying to push this through somehow. It seems like it should be fairly simple to at least show that there exists a beta and there exists a limit. Some sort of tightness and moments and just hacking around, you should be able to make it work. But we haven't yet found a person smart enough and dedicated enough and creative enough with the inner drive required to make this all work. Okay. So I want to point out one thing before I end, and that is that these altimeter compass surfaces can also be defined as equivalence classes. So remember, in AC geometry, if I have a smooth function, then essentially I'm taking flow lines of e to the I times h over chi for some chi. So I have a set here, and maybe, this is the vector field. And if I can formally map this to a d tilde, then I could ask, what do I have to do to h in order to make it so that the flow lines up here are the images, or the pullback v psi of the flow lines over here. And you see that, if I take a vector here and I rotate this by some amount, and I want to make this piece rotate by the same amount, then I have to, I just have to add the argument of the log, or the argument of psi instead of the log of psi. So as long as I take dh mapping to psi inverse of d h circ psi, and I subtract this psi arg phi prime instead of q, then everything still works. Okay, this would be true if you had a smooth function. It was a different story from the, it's not the issue comes from regularizing with small epsilons. The psi just comes from the fact that when you rotate, you have to rotate the arrows too. So it comes from a different place than q. But again, I can just define an AC geometry to be a pair under these rules. Okay, and once you have these definitions, you can start proving things, even forgetting about the geometric interpretation. So the main two theorems that I'm going to work on in the next couple times are these coupling theorems with the Gaussian free field. And these are these theorems which essentially say that in the AC geometry case, it says that drawing something that should be a flow line of e to the gamma h, and taking this as your new boundary condition, and then adding a field out here, is the same thing as just taking the whole field. And in the quantum gravity case, it'll be drawing a path here and a field independently and then unzipping it, going backwards, is the same thing as taking the whole field. And in both cases, the way you transform, here you take a free field out here, but you have to zip up. So you take a free field on the half plane and you map it up to here via the transformation rule. And over here you take a free field up here and then you pull it apart via the transformation rule. And here you get, so this, so anyhow, so these are the coupling theorems that are going to come next. And I guess I want to stress you can read this online, and there's also a paper by Julien Dubeda in 2009 that does, so he does this, the same coupling in a somewhat different way, and he also writes there a proof that these things are path-valued functions of the free field. So the free field almost surely determines the path. Whereas what we did here, and this is sort of, essentially it's in these online lectures from 2005, which you can look at, and it was the kappa equals 8 case comes from Kenyon and Schramm, although they never published it beforehand. Just showing the fact that drawing this, then choosing the field is equivalent to choosing the field. So more about that next time. I'll stop.